So I'm very glad I can speak here after a year again here at GoLab. I believe it's a nice conference and I'm happy you are here, and so am I. And today I would like to touch slightly a topic related to the previous topic, which is about designing system in distributed world, distributed systems. I will show you during the presentation how the application can evolve from like synchronous one into the one that is powered by asynchronicity. And usually it's not as easy as it seems at the beginning. Okay, is it getting better? Holding down. Okay, so let me introduce myself at first. My name is Tomáš Sedláček. I'm the developer by heart, but for the last couple of years I'm more in the field of designing systems in Datadu. If you have any questions, feel free to ask after the presentation or use the QR code in here, where is the Google form. You can leave any comment, complaint, question, and so on. So it's up to you. If you can leave some feedback, I will be very glad. So in Datadu, which is my current project I work in, we do the ETL platform. We transfer data from various sources on one side and write them for our customers on the other side. So we transfer the data, we do some transformation in the middle, and that is what we do, and our customers pay us that we do it reliably. At first, I think it was 8 years ago or so, we used to have one single monolithic application written in PHP. But soon we realized it's no longer maintainable and we need to split it up and power it and give it to some superpowers. So we rewrote the whole monolith into synchronously communicating microservices written in Go. So there was a super skilled Go application for extracting the data, another for writing data, and we need to learn them to communicate with each other in synchronous way at the beginning. They were using gRPC or HTTP protocols to communication. But then we realized, again, that when we are transferring the bigger data, we are hitting timeout, we are hitting some problems with network and so on. So we needed to learn them to communicate asynchronously. And at first, we were using RabbitMQ, like a managed service powered by AWS, and Watermill library as a tool to communicate with Rabbit, because we didn't want to deal with reconnections, reconnecting to the broker ourselves and so on. So Watermill was solving a lot of pain backs, just we used it. And then we started hitting another weird situations, which I will describe later, which we were not able to avoid, even though we were using Watermill. So we implemented our own publisher-subscriber tool, which is written and powered by Postgres, because we loved Postgres. And for our cases when there were not millions of transactions every second, there is only thousands a day, and Postgres is just capable of doing it. So we hopped on our tool, PGQ, we call it. But once upon a time, there was Orafo. Here the story begins. Orafo has a jewelry here at Ponte Vecchio in Florence. He's selling golden goods. And as a seller, he has some order process. So order process is quite simple, or it's not simple because it's order process, but it's composed of several steps which are here. So he needs to know what he is selling to who, because he must meet some regulatory limitations. He then creates order in the database, generates invoice, processes payment, does the shipping, communicates with other systems to synchronize the data. But for the sake of simplicity during this talk, let's limit it only to these 3 steps. So to get the order details, validate the items if he has it on stock, validate the customer, generate invoice, and do the handover of the goods to the customer. This is how the process looks like. It's very simple. Get the order details, create the invoice. Please know that he is doing it manually, so he's really writing the invoice. And then he handovers both items and invoice to the customer, which works, but it takes quite a long time. This thing doesn't work, sorry. So this is how it could look like in the code. In every code example, there is a QR code again, so if you want to view it or display it on your own device when you can read it better, please feel free. It will link you to the GitHub where the same code is. And this process, if it's described by the HTTP code, it can look like this. There is a server listening on some port, waiting for some request to come to the order endpoint. And when it comes, it gets order details, create invoice, and hand over the items. Each step may take different portion of time. So Orafo identified that there is a problem when printing the invoices because it takes too much time. So he found an ancient printer in the warehouse and started using it. So a new process comes into play, which is the printer. But the printer must be operated manually. So when Orafo calls this printer machine, he needs to operate it, do some manual stuff. And in the end, he has the printed invoice he can hand over to the customer. So even though this process is faster, but the customer still needs to wait a long of time, and Orafo's revenues go down because customer satisfaction is getting lower and lower. So are his revenues. So he thinks. So by the way, this is how the code looks like using the printer. So printer basically can be represented like the simple HTTP server again, listening on some other port, doing just the printing, returning the invoice. And the server, it means Orafo on the left side, he is calling the printer to print him the invoice. But when the printer is working, Orafo must wait because it's in this implementation, it's the regular HTTP call. So when the printer is working, printing, the Orafo is waiting. So he thinks how to improve the process. But before it, just sum up how does it work when the code is synchronous, because it's simple to write. Everybody usually understands it. It's simple to read and debug. The sum of the time means, or sum of the times of each function gives you the total operation time of the whole process. And unless you use some async await procedures in Node.js or Go concurrency or threads in Java, it usually is only the sum of all actions, so you cannot speed up much. It's highly I/O dependent. And on failures, you need to know if the printer, you need to react to them. You need to roll back according to the situation, or retry, or ignore the error when the printer is offline. You cannot finish the process because you are much dependent on it, and the printer is blocking you. If printer crashes, you must react accordingly, and so on. So there are a lot of gotchas, and you need to know the counterpart, in this case the printer, and its weird situation it can face. So let's try to make the code asynchronous. So at first, Orafo identified that he can buy the new printer, which is capable of printing it on his own, the invoices. And meanwhile, Orafo can do other things and serve other customers. So other customers become more happy because Orafo is serving them while printer is working. But Orafo still needs to watch and when the printer is ready with the invoice to hand over it to the original customer. So the first customer who comes is waiting, let's say, still the same amount of time because he's waiting for the printed invoice. So Orafo says, okay, let's configure this printer to smart printer, which is capable of printing the invoices automatically without my need. And this is how the process can look like. And Orafo gets the extra time he can use for other customers. So even the customers are more happy because Orafo can serve them and the whole business is growing up again. So when we compare both scenarios, asynchronous and synchronous, synchronous on the left side, asynchronous on the right side, we can see that Orafo has more time for learning Go if there are no customers there. And he can serve his customers because he has more time. So customer satisfaction goes up. But poor Orafo bought the printer, which is exploding when it gets two messages at the same time, which is some kind of memory leak every printer has. Because have you ever seen the printer that works? I haven't. So if this particular printer gets two invoices at the same time, it just crashes. We can have a look how it could look like in the code. So we'll open my IDE. I hope you can see it. Out of it failed. So in this case, if you follow the QR code, or QR codes, you will get to this repository as well. There is HTTP printer in synchronous folder, And there is a server and the printer. If you look at the server, it's what we saw before. There is an endpoint handle function which creates the invoice after we get the details. And creating the invoice is just sending the request to the printer server. And the printer server just handles the print. But there is a memory leak, which is some memory leak there. That's for the example. And I run this application without garbage collector enabled, so we can see the leak. So if I change my window to here, where the exploding printer is, I can make run, which runs the printer with limited resources. I will run Orafo server. And now, if I send request to Orafo, basically this one, it does nothing because it works when there is one invoice at a time. But now it works again because it's one invoice. But let's try if there are multiple parallel requests the same. And now printer crashed, server. It means Orafo cannot finish his job selling or processing orders because the printer is down and printer doesn't say anything about what caused the trouble. In logs, you just see print request received, some allocation formatter, printout, and nothing else. So printer is down, but we don't know why. So let's continue. There's a bug. But fortunately, there were the printer engineers who have already solved the issue with exploding printers by adding the printer queue in front of the printer. It means that in the printer queue, which can be represented like a table where there are details about the invoice parameters or invoice details and the field marking if the invoice was already printed or not. And the printer is taking the invoices or the documents or jobs from the queue on its own pace as it wants. So when the first invoice is finished, after that it takes the another, which prevents like this memory leak from happening because the printer is working based on its own pace. These queues may be implemented in many ways, like using memory, using database, using file system. It really doesn't matter. This is just the idea about Orafo not contacting the printer directly, but using the queue instead. It works nice until the queue is so big. There is a lot of documents, a lot of invoices to be printed there, and you would spend too much time printing it only on one printer. So Orafo says, okay, I need to add another printer. But here comes the trouble, because now you enter the race conditions world where you must deal when two printers start working on the same row in the table of the queue, on the same document, which may not be a problem when printing the invoices. But if you imagine some financial world, maybe you don't want to have two transactions to be subtracted from some account because you have two consumers of the table. So race condition can be the problem. Routing can be the problem. So let's imagine you have colorful printers and black and white printers, and for VIP customers, you want the invoices to be printed in color. So you need to solve and deal with some routing. You need to deal with filtering because for VIP customers, let's say you want to print the invoices at first, so they have them earlier. You need to deal with retrying. When the printer crashes, you want to try the same invoice to be printed on another printer and so on. You must deal with persistence. When the electricity is down, no printer is working, and then the power is on again, you want to continue printing when they left off. You need to deal with monitoring because you want to adapt to the situation when there is not many invoices in the queue. You can save some resources, save some energy, power by scaling down the printers. On the other side, when there is a lot of documents in the queue, you want to scale them up so you process the queue much faster. So all of these things and all of these troubles are usually solved for you by something that is called message broker. Message brokers, there is plenty of them. Some of them are open source, some of them are not. Some of them are useful, some of them are provided by providers like major cloud providers. So probably you know Kafka and RabbitMQ from the cloud provider world. There is Amazon SQS and Google Cloud pops up. You may notice IBM MQ, which is here with us since the 70s, and it's widely used in the financial sector. And even Redis you can use for PubSub and so on. Behind these is our custom tailored system message broker built-in Datadog, which is on top of the Postgres. So if you don't want to deal with and learning any new message broker and you are already using Postgres, you can use this package if you wish. And how they work? So basically the message broker is some kind of man in the middle through which the communication flows. So on one side, we have publishers and senders who are sending the messages to the broker. They don't need to know about consumer at all. They are sending messages to the message broker. And on the other side, there are consumers who can read the messages. So consumer doesn't know about the publisher anything or doesn't need to know unless you really wish. And publisher doesn't know what consumers are on the other side and how many of them. So you can have multiple publishers and multiple customers. Broker in the middle deals with routing, persistence, and all the other stuff I mentioned on the previous slides. So just let's describe in a very fast way how the publisher works. Publisher, his only concern when publishing message is to get the confirmation from the message broker. He just sends the message to the message broker, and when he gets the confirmation, his work is done, basically, in asynchronous processing. He can do it multiple times, of course, but it's usually very fast, and that's the end of his job. There's nothing else publisher should do when publishing. On the other side, when we deal with consumers are listening or subscribed to the message broker queue or topic or whatever, and they are provided by messages from the message broker. And they decide their own tempo, their own pace, how they get the new messages. And at the very end of every message processing, they should send to the message broker something which is called consumer acknowledgement. There are usually three main consumer acknowledgements you may face on a daily basis. The first is discard. It means that the consumer doesn't know how to process message, because at every processing, at the start of every processing, there should be some validation if the consumer can process it. If this consumer is accepting or knows how to parse JSONs and he gets some HTML he doesn't know what to do with, he should probably discard it and send to message broker the signal, hey, I cannot process this message, give me another. And then it's up to the message broker configuration whether such message should be resent to another consumer because it was badly routed, or if you discard it, or it should put it to some trash or alternative queue or so. The second acknowledgement is just acknowledge, which means I process the message, I can get another. So by doing acknowledge, consumer says to broker, I'm okay, I'm fine with processing, I've finished, give me another. And there's also negative acknowledge, which means during processing some error happened. And then again, according to the message broker configuration, message broker sends it usually to another consumer, which may have the better luck. Here's how the process works. I think I will not comment it much because it's the first part when the client who is sending the request doesn't get any information about how the whole processing finished. So it is some kind of background processing described here. So consumer consumes message, sends the acknowledgement, and that's the end. If the client needs some confirmation, it's slightly more complicated because the consumer before echoing or not before echoing usually must publish the result to some result queue, then do the echo. Because if something crashes during the publish and you would echo, you would never see the result. So he publishes the result, and then there is some consumer who is consuming the response queue. It may be the same service who was accepting the message originally, who has some connection to client. And if you imagine some eShop order, on generate order or create order, here we can have the generate invoice. When it goes here, you just be using WebSocket or any other communication channel. You can send to the client, to the browser, hey, here's your invoice. And the client doesn't need to wait the whole time this proceeds until he gets the invoice and see some loader button or progress bar. So he can use your application even though in the background you are generating the invoice. Okay, so another demo or example where we replace HTTP communication with with RabbitMQ. So here is the code. Again, there is a server which is quite the same, but the only difference is when generate the invoice, it doesn't call the HTTP server. Instead, it creates, in this case, connection to RabbitMQ and just publishes using the publisher and using Watermill. It publishes the message to some printer queue, and that's all. It doesn't care about if the printer is on, if it's off, if it's working, how many printers is there, and so on. It just sends the message to some channel, to some queue or topic. On the other side, the printer, which is consumer in this, even though it still has memory leak because it's a printer, it handles the messages, and on every message, it creates a subscriber, again using Watermill, and on every message, it just parses message. Ideally, here should be an egg, but it's not there. But discard, but it's not there. And on every message, because we follow the happy scenario, it says print message proceeded. So it means invoice was generated and sent to the client. And this is the lifetime of the printer. So it just consumes the messages, and it doesn't know anything about the server, about this publisher at all. And if we run it, it's this one. Clearly didn't work. So I will make run. Again, it's a run with limited resources, consuming the printer queue, and make run on the server side. Oh, publishnet. Okay, I need to stop this server first. There is a clash of on ports. Okay, server is running. I will open my command center and send one request. You can see, even though there is 2-second sleep, I can send multiple messages, even with the AB, a lot of messages, all accepted, or all are marked as order processed. And meanwhile, in the background, the printer is printing one by one according to my configuration, what I told it. And there is no memory, out-of-memory error. So let's get back to the presentation. Okay, so we saw how easy it is to use the asynchronous version. It just publishes and consumes messages. But it's easy, usually, until you face some pitfall in production. So theory is nice, but you know what happened to our it's very close to my topic, because what happened to our consumers that exploded. So if you are running application in some controlled environment where you have resources limited, for instance, 8 gigabytes server, and this is your application consuming some memory over time, it's okay unless you hit the limit. When you hit the limit, it crashes. And because it's out of memory, it cannot lock, it crashed. So you usually don't have any error. You can look into the Kubernetes what happened to node, but usually it's not easy to find that OOM happened, but it happens. So you should be aware, but it is a simple scenario, but often in Kubernetes world, there are multiple pods on the single node, and you must count the sum of all processes running on that node. And if their total sum is over the limit of the node, it crashes, all the application crash. You have no information in the pod why it crashed, because it cannot log it because it was out of memory. And weird situation happen. And weird situation happen even though when you are using RabbitMQ. And this is what we are facing a lot. And in this case, we have a RabbitMQ broker, and there is some message with the back inside producing or causing OOM out of memory. So such message is consumed by the consumer A. Okay, so he doesn't know it's rotten message, so he starts consuming it. Soon, he gets out of memory because of the memory leak. So the consumer crashes. And because there is no connection, because consumer is down, RabbitMQ says, okay, this consumer is down, I will terminate the connection, and I republish the same message to the consumer B, which is like expected behavior for majority of the situations when the failures are under control, not when it's OOM. So the consumer B gets the rotten message, and his destiny is the same. He ends with the OOM. And again, Rabbit broker sees, okay, this consumer is not responding, it failed, the connection is lost. I will republish the message to the consumer C. And here it goes and goes, it's in an infinite loop. If you have limited number of consumers, you will soon be out of consumers because every one of them will be OOM killed. But if you are using Kubernetes with replica set enabled for, let's say, number of 3, Kubernetes will save you because it will create new consumers in infinitive loop, so you have always the 3 there. So the one message will hit your consumers and make them OOM in infinite loop until you stop it. And stopping it and identifying this is not so trivial, because usually from the logs you don't see nothing, because there is just pod is down. In Kubernetes you can see the node is down because it's down. And you must deep dive into some other logs where you can see the reason why the node was crashed. But on the first side, usually at least in our company, on the first side, we could identify it by looking into the metrics, where we could see when there was memory consumption going down and going up and never down, it was the memory leak, memory crash, OOM crash when consuming message. And here again, the RabbitMQ republished the message to another pod, it crashed. So it illustrates what was happening in our infrastructure. How to deal with this is not so simple, because as RabbitMQ keeps republishing the messages, you must stop all consumers. You must prevent Kubernetes to creating new pods. Find in the queue which message is causing it, which might be tricky because you see the payloads, so it can be any message which is in the queue at the beginning. Discard this message, remove it from the queue, and start the consumers again. So when this happens in production and you see it for the first time, probably it will take you some time to do it. So this is the first what we faced and what was why we were pulling our hair out of our head because of. And the second was the deadlock on deliver acknowledgement timeout, which means something very similar. But in this case, there is not like a rotten message, but there is very slow message which takes a long time to process. And when consumer A gets such message, he starts processing it, and it makes a lot of time. But there is a consumer timeout in RabbitMQ. I think default value is for 25 minutes or so. I'm not sure. And in 25 minutes, if the message is not processed, the RabbitMQ decides this consumer must be down because it's not responding in 25. It didn't respond in 25 minutes, so I will kill the connection and pass the message to another consumer. But this consumer is still working on them because it was killed the connection on the other side. And where we were using Watermill, we were using a channel, which is like slighter abstract of the connection. And we know what is happening, but in this state, we were not able to send some heartbeat to the RabbitMQ telling, hey, I'm still here, don't kill me. Which was not good, because this was happening. Consumer C started processing message. Again, it took some big amount of time. Then message broker stopped the connection and retried the message to consumer C, which has the effect that all 3 consumers ended with the same situation. All of them processed the message, even though it took them a long time. And they sent 3 results, or the message was processed 3 times, which, again, probably you don't care when printing the invoices, but when you are processing some payments, you probably don't want to send money 3 times instead of 1. So this is the consumer acknowledgement problem we had. And it was mainly caused mainly caused that we were not able to send a heartbeat to message broker, not to kill this one. And we were not either able to change this configuration parameter because we were using managed instance on AWS, and this configuration parameter is not editable in there. You can change it when you are hosting your RabbitMQ and managing it on your own, but you cannot change this parameter on AWS, so bad luck for us. These two things led us to implement PGQ, where we have nice visibility about what is in the queue, how long it's in the queue, if it was retried, to apply to set the limitation how many messages or how many times the message can fail on OOM, because every, let's say, start of consumption increase some counter there, so we know if some message is consumed for multiple times and prevent this from being consumed again. So if you want to give it a try, the PGQ, here is a short YouTube video which will explain you what you get. But this talk is not about the PGQ. You can try it on your own. Here is the code. By the way, PGQ I presented here at GoLab last year. So if you are interested in that, watch the video from the last year. There is the same demo I would show you now, but I am running out of time, so we will skip it. But at the end, sum up where is the asynchronicity helpful. So asynchronicity, of course, isn't like silver bullet you would use anywhere. Sometimes you need to, when you call some function, you need a result and immediately in the next step. So in this case, it's convenient to use synchronous code and avoid asynchronous because you need the result immediately. So it would be only the complication in your design and your code to use synchronous code. But when it's good to use it is, for instance, order processing systems like Orafo has. When there is a lot of process steps needs to be taken, and some of them can be done in the background, like communication with and synchronization with ERP system or CRM systems, or ordering shipping, ordering payments, processing payments. This, if it makes sense, can be done asynchronously, just passing from the main thread the signal somewhere else, passing the data, and the other side knows how to handle it. And you, in your main process, you keep it much faster, and your user can do like, mainly when you are dealing with some UIs, when interaction with users, your application will look much more faster and smoother because a lot of background processing will be done in background. So that's basically what I told now. So file processing, generating invoices, reports, anything what you don't need immediately in the next step can be run asynchronously. What is good when, or another feature of what asynchronicity brings to you is decoupling microservices. So when we had Orafo and printer, when it was asynchronous, Orafo didn't need to know nothing about printer, because if the printer is down, the order still can be finished, even though the printer is off or doesn't work. Because Orafo is only communicating with the message broker, and it is the only thing what he concerns about. If he can publish the message, and if it's processed sooner or later, he doesn't care. So decoupling microservices is very helpful, and it helps you to scale the systems and scale the parts of your system accordingly to your needs. In DataDo, we do ETL, and sometimes the jobs may take seconds, which would be no trouble with customer acknowledgements we are facing, but sometimes we deal with data processing, which can take hours, and then we were hitting the timeouts on the acknowledgement side. But of course, if you can tune it, it's much better than display some loading button or loading bar for 2 hours to customer. Load balancing and scaling, and because it's decoupled, it's much easier to just scale the consumers according to your needs. You can configure it to scale according to the queue length and so on. Real-time notifications like sending emails, it's the good use case for asynchronous communication. However, it's not just ping, because sometimes it brings the shadow into your code, which is some hidden complexity. You need to, as it's communicating asynchronously, you may deploy a new version, which version of the application on the other side does not understand. So you should avoid some breaking changes and so on, because it can harm you. it is usually harder to test because of and debug because publisher just publishes somewhere and it really doesn't do nothing. Some errors only happen under some circumstances as consumer acknowledgement. So when the job takes a long time or is producing out of memory, when you face race conditions when you start using asynchronous code and possibly deadlocks you need to tackle, which probably you don't need to fight with so much when you are writing synchronous code. So when deciding synchronous or asynchronous, as usually in IT, it depends. So you should consider what your system you are building, what constraints you have, what requirement limitations you are having, and so on. So it's not an easy and final question. Asynchronous is good. Use it instead of asynchronous. It really depends on every scenario. But sometimes you may identify that it may significantly make your processes more reliable and much faster. Doesn't work again. So if you are interested in the asynchronous processing topics, there's a very nice article. There are very nice articles, and it's even a printed book. If you are a fan of printed books, and this is called Enterprise Integration Patterns. Here is the link. I encourage you to use Watermill, or give it a try to PGQ if you are eager and you don't want to learn anything about RabbitMQ and you want to just stick with Postgres. And big thanks to this repository where I usually, for my presentations, take my Gopher, but the Gopher icons from. And as you can feel, I'm nearly OOM. So I'm now happy to answer your questions, or if you have any comments or feedback to me, feel free to use this QR code and leave the hate or complaints there as well. And if you leave your email, so I can reply you back. Just if you leave your email, I will reply you back. Otherwise, it's asynchronous and I cannot deal anything. Okay, so thank you very much.
Okay, thank you for your talk. Are there any questions? Oh.
So, hi. Usually with the ACK timeline issue, we've ended up just ACKing the message early, and then before you process it. And
it's an option, but when it fails, you have it ACKed, so it cannot be retried because from the message broker, it's like processed.
Yeah.
Is this something that if it was in some scenarios like sending emails or such, it makes sense. But when we are processing some financial data, there is no go in this field.
Yeah, thanks.
Any other questions? Oh, yeah.
Thanks for the talk. So I wonder if you consider using Watermill SQL before developing PGQ, and if so, what features PGQ has that make it distinct, that make it a better choice?
Yeah, I realized there is a SQL in Watermill like 3 months ago, but we were implementing it 4 years ago, and I'm not sure if it was there back then. So that's the reason why we implemented it on our own. In the end, it's just one simple SQL query behind of the consumer. So it was not really tough to implement it, and we knew we will just need this one technology, so we implemented it on our way because we knew we don't want to get back to use RabbitMQ, so that's the reason. But 4 years ago, I think SQL was not there as a Watermill provider, if I'm not mistaken.
Thanks.
But maybe I can react to the question regarding the databases, the separation of databases, because we use one single database like for the application, and the second database just for the queues. So one instance of the database is widely used by all of the applications for the queue mechanism as a message bus, and in the same, let's say, database instance, but in different database or schema, there are data for applications by applications, like each application has its own.
Thanks.
Any other questions? Oh, yeah.
Thank you. So I have a question. Did you consider to configure Develer queue configuration? Is it supported in ActiveMQ? Because I use SQS and that's supported there, so it prevents the problem that like all your consumers would fail on this corrupted message.
Yeah, that letter queue I think you can use when you are not hitting OOM. When you discard message or neck it, then you can configure it to go to this alternative queue or to this trash queue. But when it's OOM, there is no signal, no like consumer acknowledgement from the consumer side to broker, and the broker doesn't know what happened, and it doesn't change like any. If you reject it or discard it, there is some counter which gets higher and higher on each occurrence, which you may use to identify that this message can be routed to the garbage queue, but not in the OOM case because the broker doesn't know how many times it was processed.
Yeah, I think it depends on implementation of if the broker it knows that that message went somewhere, then it can maybe count. At least in SQS it was not the issue even this out of memory.
Yeah,
I think.
in RabbitMQ it doesn't know. It knows after the after neck or reject. Maybe in PubSub or Google PubSub they do it in advance. I'm not sure we haven't used it.
Okay, thank you. And one more question. So with Postgres, did you have any performance issue? Because as I know, these SQL databases, they're not really designed for these data access patterns where you have like many inserts and then you need to delete many messages and then probably you need this vacuum.
Yeah.
And
I haven't done the like proper performance test yet, but when comparing with the RabbitMQ, the publishing was quite the same, like 10,000 messages published on both in 1 second. In PGQ, the bottleneck is on the consumer side. It takes a long time because we are pulling the messages from the queue, and this is what is much slower than when comparing to RabbitMQ, let's say. But in our case, we haven't faced it because our jobs are minutes, seconds, or even hours long. So if the polling takes 2 milliseconds, and we really don't care, and we are just fine with that. We are even sending emails or notifications to the API we have. So we haven't faced the bottleneck yet, but for sure, if our platform will grow up, probably it will be the problem. But right now, we are handling hundreds of thousands of messages a day, and there's no issue. But it's not for every use case. If you know that you will send emails and you will need to send them a lot of them, then probably PGQ is not the right choice for you. You should stick with a proper message broker.
Okay. Any other question?
Okay. Thank you very much, then.
Yeah, that's it.